Hi, my name is Rick Fontenot. Today, I'm going to be presenting some of my research findings on ensembling. I'll give an overview of what ensembling is, go through how to approach it with a demonstration of a case study, as well as give some summaries of some interesting research by others in the realm of deep ensemble learning. So this is a summary of other research on ensembling. And there's what's known as traditional ensembling as well as ensemble deep learning. And you could see this kind of rapid rise in research around traditional ensembling around 2012 and then just kind of skyrocketing as of late. Whereas in ensemble deep learning, it's just now emerging to kind of take over in this research world as perhaps the next big area of research. And many of you may be familiar with this already, but ensembling is very popular in competitions, Kaggle and others. This is a slide from Professor Slater in one of our classes showing the majority of top-ranked models in the competitions include an ensemble of multiple base learners. I have a counterpoint, bring a quote to you here from Philip Tanner, who's the CEO of DeepChecks, and they do a lot of checking and monitoring of machine learning models. And he said that while ensembling is really popular in competitions, that he doesn't see them used in production in the real world quite as often as you'd think. And some of the reasons for that would be it's expensive. The compute overhead and the training time can be really significant, not just initially, but if you need to regularly retrain your models or you need a fast real-time prediction that relies on retraining, that can be a limiting factor in whether you get to use deep ensemble learning, ensembling in particular. There's also a lack of explainability, even if the models, the base learning models that you feed into an ensemble themselves are explainable linear models. Once you ensemble, it's trickier to be able to explain the modeling and outputs. But there's still value, and I certainly appreciate it more after this research. So to briefly go over what ensembling is, if you're not familiar, generally, it's when you are approaching a problem, you might evaluate different individual models. You might do a linear regression. You might do a neural network, and you might do a random forest. Even if you end up with a complex model, you're usually checking a couple of simple models, whether for explainability or just to set a benchmark. You have these base learners available to you. And ensembling is the method of combining all of the predictions from all of your base learners in a way that can give a better prediction by combining all these models together. And the chart on the right here is showing that generally, you have an average between your models, and then the dashed line there in the middle is the best individual model you have. But if you do this ensembling to combine them, all of them together generally produce better results, meaning higher accuracy, lower loss. And so what I want to talk about next is what are these combination methods? How do you combine them? And there's multiple ways. If your use case is making a numerical prediction and you have multiple models, you could simply average together the predictions of all of those models. You could also, instead of a simple average, do weighted averaging based on domain knowledge or just insight you've gained from studying predictions on a validation set. In classification problems, you can have a voting process if you have all of these models, these base learning models. There's majority voting, and whereas if any one of the classes gets more than half of 50% of the votes, that's your final prediction and combination. But that if one doesn't get 50% of the votes, you have another set of rules based on to determine what class they get. And there's also plurality voting, which is simply the one with the most votes. And then similar to regression problems above, you could do weighted voting or you can do soft voting. But what I find more interesting to research, because it's a little more complex, is a meta learner. So you can combine these things with another model altogether. And this can be done for numerical or classification predictions. And so here's what a meta learner process looks like. You have your training data and you build multiple individual models. If you have a classification problem, you might look at logistic regression, random forest, XGBoost, and a neural network. And with each of those models, you get the predicted probabilities for the classes out of them. And instead of simply averaging or voting them, you feed these probabilities into a meta learner, which could be any machine learning model. The meta learner could be a logistic regression, it could be a neural network. But the inputs to this learner are not the original training data, but the predicted probabilities that each of these models make. And that becomes the input to your second level learner. And then from the using the meta learner, you combine them to make your final predictions. And that's the combination method. I'm not showing it here, but there's more complexity. This is a second level meta learner. You could go an additional level and have multiple meta learners and feed them into a final meta learner. But for today, I'm going to focus on kind of this workflow with a single meta learner to combine the base learner models. Now, part of my research was you learn about new models and then you want to figure out, how do I achieve them? How do I implement them? What are the assumptions? How do I need to prep the data? And what assumptions do I need to meet going in? So combing through some literature, I've tried to kind of combine some assumptions and best practices. And the first one is that you need out-of-fold predictions. And by out-of-fold, I mean, if you train a model, if you've split your data set into a training and test, you can't simply make predictions on the training set just based on the model you just trained, or it will overfit. You need, and I'll show more on this, but you need out-of-fold predictions. That can be done by making predictions on a validation set, and the validation set is what feeds into your meta learner, or you can go through folds with your training set. And that involves retraining each time to make predictions on a holdout set until you get predictions for all of them. But out-of-fold predictions are one of the key components of ensembling. Another assumption or best practice is that you need model diversity. While it may be intuitive that you want to feed like really good base learning models that have high accuracy and then combine them to get it actually it can be counterproductive to do that. If all of the models are making the exact same predictions, combining them together, you're not going to get anything different. So diversity is important. If you have gone through this process and you're like, well, I'm going to just do a logistic regression and a random forest to start, and they have relatively low accuracy, and then you have a more complex model that has a high accuracy, you may think, well, those original ones aren't good enough to include. And that's kind of counterintuitive, but that diversity is really what makes the ensemble. So you need good models to start, which means relatively good accuracy or low loss, but the diversity is important too. And kind of the last one I'll cover here is about pruning your ensemble. Just like if you weren't ensembling, you're just building an individual model, feature selection is important. If you put in a bunch of variables that aren't good predictors of your target, then you can be overfit, or you can have just lower performance with extraneous variables. So this is a similar idea than if you have 4 base learners or 20 base learners, just grabbing them all and throwing them into an ensemble may not be the best approach. You need to kind of select which models are the best and give you the best ensemble results. And another benefit of that is, instead of throwing 20 base learners into an ensemble, that's really resource intensive, both in the training time and computational resources. So if you can reduce it down, not only will it improve the predictive performance of your ensemble, it can drastically reduce the amount of overhead in building the base learner and ensemble combination. Now, within pruning, there's kind of a debate and not a clear best practice on what order you add models to the ensemble to determine the best mix. One obvious way is start with the one with the best performance as far as best accuracy or lowest loss, and then add the second one. And so this is kind of ranking them by loss or ranking them by accuracy. But as we discussed previously, diversity of models is also important. And so another method of pruning would be to rank your models by order of diversity in their pairings, and not necessarily worry about the best performance, but start with diversity and keep adding until you get to the best ensemble. This is a kind of a chart of that pruning process. And what you'll see here, what you'll see here is this solid line it's starting with the best individual model, and then you're adding another base learner to the ensemble, adding another, and you can see that the loss is going down as you're adding more, and it kind of flattens out and plateaus. Now, this solid line represents just a random ordering of your base learners and how you add them to your ensemble. The dashed line is what you can get when you order your base learners. You can order them by loss, you can order them by diversity, but you can see there, as you add learners, you actually get to a lower point if you were to add them in the right mixture. And then again, at a certain point, the more learners you add, it may be overfitting, and the gains you got from ensembling kind of reverse. And so this is a way of showing the optimal number of individual learners. And if you rank them in an order for pruning, you'll have better success. So taking all of that, I wanted to go through a demonstration, not only for myself to kind of look at some of these assumptions and the effects of them, but also to present that here. I'm not going to do a code review, but please contact me if you would like to see the code or discuss it. Today, I'm just going to discuss the results of that and how it relates to these assumptions and best practices. Now, the case study that I'm going to go through is anonymized. It's an anonymized data set, has 45 numeric features and 5 string features. So there's 50 features. The target is binary and it's also anonymized. So this client wants us to make predictions on this target, which is transactional based for them. And they have given us a cost function where if they have incorrect predictions, it costs them on average $100 for a false positive and $200 for a false negative. So the goal of this is to minimize their money lost. I'll track accuracy just so you get a feel for it, but keep in mind the metric here that we're trying to minimize is the money lost. Similar to the diagram I showed before, with this data, I created 4 base learners: logistic regression, random forest, XGBoost, and neural network. I made, with each of those models, I made predicted probabilities for the classes, fed them into a meta learner, which was built out of a neural network with 5 dense layers, each with 300 neurons. So this is the diagram of the ensemble for this use case. Now, each of those base learners had quite a bit different results. I'll start with the cost. This is the money lost per transaction on the test set. And this list is ranked by the best performing models that minimize the loss. And neural network was the best individual model, and it got this money lost per transaction down to $4.13. At the same time, you can see its training time of around 20 minutes is significantly longer than these other 3 base learners. After we've trained those models, making a prediction on a validation set the time on that is negligible, less than a minute for all of these. Now, if we wanted to do holdouts and make out-of-fold predictions on the full training set, which is a much larger data size than the validation set, what I'm showing here is I did a 5-fold process. And the training time to get these out-of-fold predictions is about 5 times what the original training time was. You're training it for 4/5 of the set and making a prediction on the holdout, and then swapping and doing that 5 times. So you can see on the neural network, getting those out-of-fold predictions at 82 minutes is just astronomical compared to the others. Again, that 82 minutes may not sound unreasonable, but this is, a small to medium-sized data set that is exacerbated on bigger data sets or more features. Now, I mentioned the time it took to make those out-of-fold predictions. I kind of wanted to show what that looks like on the in-fold versus out-of-fold. Again, in-fold is you train a model with your full training set. If you directly make predictions on your training set with that model that it was trained with, it's overfit. And what's interesting, and then if you were to do this holdout process and get the out-of-fold predictions, something that is interesting here on a linear model, you can see these predicted probabilities. This is predicted probability of class 1, and the colors are by its true category. And you can see that they're very closely related. There's a little bit of spread across here. So the predicted probabilities on an out-of-fold is a little bit different. But what's interesting is you get to more complex models that are more prone to overfitting. You see a lot more separation here on the random forest. On an in-fold, you can see if you drew a cutoff here vertically at about 0.5, it's almost perfect because these predictions are made on the data that was used to train it. It's like the cheat. Whereas if you were to draw it horizontally on the out-of-fold predictions, you'll notice the probabilities kind of above and below the line here of the opposite classes. And on a neural network, here on the right, it gets even more complex, same idea. But this is just to give you an idea on how big of a difference you can get on these predicted probabilities rather than just a class 0 or a class 1. Next, these are some results from the first attempt at ensembling with that neural net meta learner. Just back as a reference, the first item here is just an individual neural net base learner, no ensembling. Our money lost was $4.13 per transaction. The first ensemble was done with in-fold predictions, intentionally violating kind of this assumption that I've laid out. And you could see that the money lost, more than doubles. So if you use the in-fold predictions as your input to the meta learner, it's going to be bad news. So this is just a reference to show how big that impact is. The next two are really interesting to me. The third one is an ensemble with out-of-fold predictions that were made on the training set Remember I showed it took a lot of time to go make those out of fold predictions on this training set by doing 5 holdouts. And this is including all 4 base learners, the money loss got down to $3.94, which is better than our individual model was. But what I also found interesting here was that instead of spending that time to create out of fold predictions on the full training set, if I just made it on a smaller validation set, the sample size there is still, roughly 16,000. That seems to be sufficient for this meta learner. And the money lost was, again, $3.94, so about the same. So this may be an instance of may not need to spend all of that time getting out of fold predictions on this full training set if the data you have to work with is of a big enough size. Next, I wanted to look at this this pruning process. And on the original slide, I showed the individual base learners and kind of their ranking, with neural net being the best, down to logistic regression being the worst performer out of the 4. But what I've got here on the left is a correlation matrix for those predicted probabilities of each of these models to get an idea on the diversity. So while pruning exercise 1 here is ranked by what's their best performance on the loss, which one has the least loss to the highest. The second pruning example is ranking them by diversity. So it's again, the neural network performing so much better than the rest, and got that as the first model in the pruning process. That's the one we start with. And if we look at diversity, while logistic regression may have had the highest loss and been last on the list in example 1, it actually has the most diversity in these predicted probabilities compared to the neural network, followed by random forest and then XGBoost. And lastly, just kind of as a baseline, pruning example number 3 starts with a neural network again, and then the others are just randomly ordered. So these are the results from this pruning process. The chart here is showing the money lost per transaction on the y-axis. You can see how they all start at the same point with that individual learner, which was the neural net base learner. There's not really ensembling. It's an individual base learner. Now, as you add them, the blue line represents just the random order. And you can see, you add a second one, and the loss definitely went down. You add a third, it went up, and then it kind of flattens out. Diversity, ranking them by diversity, on the green line, you can see it continues to decrease, and its best result was including all 4 base learners. But what was interesting is the orange line, which is where we ranked them by the best loss, starting with neural net. Then add XGBoost to the ensemble, and it got significantly lower on the money loss. Then as we added the last 2 models, it increased again. So this is kind of a demonstration of that textbook chart a few slides back, where just using all 4 base learners may not give you the best performance. Ranking them in these orders and going through this pruning exercise shows that using an ensemble of just neural net and XGBoost gives the best performance meaning the lowest loss. And then it also means that you don't have to train and include these other 2 models. So you've reduced the amount of time you need for retraining and making predictions. Kind of tying all of those together and just comparing. So I wanted to compare not just the money loss, which we've looked at above, but also this kind of idea of total modeling time, meaning here's our individual neural network. We said is about 20 minutes. The money loss per transaction is $4.13. And then looking at kind of these best or these 3 approaches to ensembling. If we use all 4 base learners in the ensemble, and we build that meta learner with out-of-fold training from the full data set with that 5-fold process, it takes over 116 minutes. It takes a really long time, although it did improve the money loss. Now, just remember, if this modeling time includes the time to train all of your base learners, make out-of-fold predictions on all of your base learners, as well as the training time for the meta learner itself, which in this case is really small. It's about roughly 2 minutes on all of these. Now, if you do the ensemble with the out-of-fold predictions just from the validation set, instead of going through that expensive time to get it on the full training set, and you could see it's only 24 minutes, only slightly more than the individual neural network without ensembling. And its money lost was the same as if you spent all of that time. But then with the pruning process, it's showing that if we reduce it down to an ensemble of just the neural net and XGBoost, omit the other base learners, it only adds about 3 additional minutes of training time. And based on for this case study, it saves about $38,000 annually. So that's a pretty big savings for 3 additional minutes of training time. Again, this will change based on data size and use case, but this is kind of a confirmation of those assumptions coming from the review of texts. And so let's kind of recap where we're at so far. These out-of-fold predictions are absolutely critical. Good models with low loss are also really needed, but don't forget model diversity. It's important too. And going through this, this pruning process on your ensembles, not only can it improve, like make a better model, it can also save time. Can reduce your training time and your compute resources. And then don't just assume that you have to make out-of-fold predictions on your full training set. If your validation set, it has a large enough sample size to make a good meta learner, then you may be able to save time there. So just think of that. You need out-of-fold predictions, but how many? And that may change based on from case to case. So given all of that, you could see these time constraints, why deep ensemble learning can be a challenge. Back to the beginning of the presentation, some of those concerns about compute resources and the amount of time to retrain. It's challenging. So what's happening in the realm of deep ensemble research? And I wanted to go through a few papers that I found really interesting, completely different approaches. The first was a paper on Alzheimer's disease neuroimaging. And one of the challenges with these brain images is that it's super high dimensional data. The number of images and pixels in those images, it's a high volume of data for each record. But there's a small number of samples available. And in this industry, in order to make these first level models interpretable, a lot of these features, if you think of the features as pixels in an image, they aren't really needed or don't have, if you were to go through feature selection, they're just, most of the pixels are not important. So in this industry, one of the common things that is used is this sparsity inducing regression, which is a way to kind of zero out the pixel features that are not important. And when they do this, these multiple sparse regression models, one of the key things used there is the regularization parameter. And what they did with these images is they built multiple sparse regression models, all with different ranges on the regularization parameter. And then they took the outputs from these models. So again, there's very similar models, all they're changing. While I showed logistic regression, neural net, random forest, all of these things, they're using the same model, but only varying the regularization parameter. And then they take the outputs from these sparse regression models and feed them as inputs into a convolutional neural network to make the final predictions. And Similar to my use case where accuracy wasn't important, I was worried about this money loss. In this industry, sensitivity is really important because a higher sensitivity score means lower chance of misdiagnosing patients. And their ensemble method improved the sensitivity by 4 to almost 8% compared to previous modeling research with other methods, individual models in the same subject. So just an example of your base learners don't have to be a bunch of different kinds of models. It might be just the same model type with different hyperparameters, different regularization parameters. So keep that in mind. The next paper that I want to review, it seemed really interesting, was an ensemble of classifying vehicle types from these kind of traffic surveillance sensors. Now, as you can imagine, like one of their first steps in this research is highly imbalanced. Some types of vehicles are rare and some are more common. So they balanced with augmentation. But then they made multiple convolutional neural network models for these vehicle images, and they trained them with different residual learning frameworks: ResNet 50, ResNet 101, ResNet 152. They kind of leveraged these residual learning frameworks, and rather than say which one is the best, they trained kind of identical models with the different ResNets, and then they ensembled the results of those. And it's kind of interesting here is, I on the use case example I went through, I used neural network for the meta learner. This is an example of using, really complex models for their base learners. But then they just used a maximum voting policy for the combination. So there's not a meta learner, they just use maximum voting policy to combine these three. And this is a chart of their results, and you can see a significant increase in the precision of their ensemble of these three compared to the best individual model, which was using ResNet 152. So where the deep comes in this overall diagram of ensembling can come in different places. It can be at the beginning, and then simple combination methods. This last one that I want to review is the one that kind of blew my mind the most. And this group created what they called snapshot ensembles. And the idea is that in neural networks, an ensemble of multiple deep neural networks is more robust than an individual model. But creating a bunch of individual neural networks is expensive. It takes a lot of compute resources and a lot of time. So that may be one of the reasons that you don't see a lot of ensembling of multiple deep neural networks. But there's kind of a brilliant little idea in this paper, in this concept. When you are training a neural network and you're trying to minimize loss, kind of following this gradient descent down, you're looking for a minimum. You're going to hit a local minimum, but you're looking for this global minimum eventually. And so when you're fully training a deep neural network, you're trying to keep going until you find that global minimum. Now, to do that on a bunch of networks is expensive, but these guys had the idea of, well, what about all of these local minimums? Even though these local minimums may have similar loss, the errors that they make on the predictions are diverse. They're different. If you were to stop training at 10 epochs and then compare it to 50 epochs, while the error rate may be the same on a item by item basis, there's actually quite a bit of diversity in it. So their idea of snapshot ensembling was, instead of fully training a bunch of individual deep neural networks to ensemble, what if we only train one? But what if every time we hit a local minimum, we stop, we save that model, and then we continue, and then you get to the next local minimum, stop, save that model all the way through until you get to fully trained what they believe is the global minimum. But now you have maybe 5, depending on how often you stop and capture these snapshots at the local minimums, you have multiple models that are diverse, could be ensembled, but you've only trained it fully once. And it's kind of a fascinating idea. And their findings were that the snapshot models, when ensembled, they yield lower rates than just one fully trained model, and that they compared pretty favorably to ensembling, say, 5 individual neural networks that took 5 times as long to train. So I wanted to show a little of their output and results. On the left here, you see a comparison. Now, they're showing the error here, kind of the opposite of accuracy, so 1 minus accuracy. The single model had error rate of 24, but even just ensembling 2 snapshots of a single model got the error rate down. The other thing that's in it, and then they went on and collected more and more snapshots and did comparisons. And the chart on the right here is interesting because it kind of shows an example of pruning. It's in a table and not a chart, but this M represents the number of snapshots where they paused and saved the model at a local minimum as they were fully training. And you could see the error rate going down as they add more snapshots until a certain point where at 8 snapshots kind of gave them the best rate. And then at 10, you see it start going up again. So just this fascinating idea is these snapshots and ensembling them is improved, but just a reminder, here's another example of why that pruning is important. Don't just capture 10 or 20 snapshots and put them all together. And lastly, this is their chart comparing it to an ensemble, a true ensemble is what they're calling it, of multiple individually fully trained neural networks. That's the black line. So the blue line here represents the error rate on just a single model. No snapshots, no ensemble. The red line represents the error rate on an ensemble of their snapshots. So this is as they're adding more snapshots, the error rate's going down. Now, the black line is, okay, now they're adding a second fully trained neural network, a third fully trained neural network. And you can see the black line, yes, it gets to a lower error rate, but as you go across this, keep in mind that by the time you get here, they've trained 6 neural networks. And so it's 6 times the training time. This red line is just 1. They just captured snapshots along the way. So it shows a good improvement by ensembling these snapshots compared to just a single fully trained model. Didn't produce quite as low error rate as a true ensemble of fully trained neural nets, but at a much, much lower training time. So this is kind of a fascinating idea on one of the holdbacks with deep ensemble learning is the resources it takes to do it. And this is one method of kind of creating that ensemble without adding a bunch of training time. So I appreciate your time. I hope you found this helpful. And this is a list of some of the references that I covered here. If you would like more information. And then kind of back to the beginning here. If you have any questions or would like to talk about this research more, you can email me, rickfontenot@gmail.com. Thank you for your time.